Hi everyone, this is single step synthesis. We are looking at how to make the functional groups, and we're going to look at the first three reactions today: addition, substitution, and elimination. Starting with addition, you had a little bit of a preview with this one with your polymer lessons. These are atoms that are added to double or triple bonds. So we will know by seeing double and triple bonds that we are doing addition reactions. So a C double bond C is most common, but I will show you reactions with triple bonds as well. You'll notice here that in red I've said two compounds form one product. Again, this is a really convenient way to know whether you have addition. So on the reactant side, you're going to see multiple bonds. On the product side, you'll only see one. And this is fairly unique, this sort of combination. So we'll be using these for alkenes and alkynes, and we're going to be forming alcohols, not primary alcohols typically. I'll talk more about that later. Halogenated hydrocarbons. Halogenations are the halogens, so putting things like chlorine, iodine, bromine, things like that onto your carbon. And you can also make alkanes with this method. So the general reaction looks like this. We have a double bond. We're going to break open that double bond and flip it up. And then there will be two new things to put on, which is the X and the Y. So again, we can do lots of different things. These are the main things we do when we do addition. We can add H2. This will turn our double bond into single bonds, so this is a convenient way to make it into an alkane. We'll see that we'll use this when a double bond doesn't suit our needs and a single bond is actually easier to work from. We can add diatomic halogens, we can add water, and we can add hydrogen halides. Probably a common one here is going to be the water, because this is going to put an HOH on, which means we're going to be able to make an alcohol by adding water. So let's have a look at some examples of reactions. This first one is an addition of hydrogen. So we have our double bond to start with. I'm adding hydrogen this time. And what we're going to do is, again, break open that double bond, and we'll have two new places, one on each C, to put an H. You'll notice I've just drawn the H's structurally around the C double bond C. That's just allowing us to see a little bit more what's actually happening in that location. And no matter what else is happening in this carbon chain, if you're doing an addition reaction, the action is going to be at the double bonded C. So you could have a really long carbon chain, for instance, or even a substituent on there, and it's the C double bond C where the action is going to take place. Here's an addition of a diatomic halogen. This is called halogenation because we're putting halogens on. So again, same process. I'm just going to break open that multiple bond and put the Br2 in the two new spots that flip open, kind of like a trap door. Ideally, this would be all on one line, but I started it kind of in the middle of the page, so mine is going to the next line. This next example is the addition of water. We call this hydration, and I'm going to keep this one really simple with just a 2-carbon structure, and then I'll show you a little more complicated with a 3 or more complicated structure. And there's a little star here because there's a rule that has to be followed when you don't have the identical things going onto the double bond. Now, there's only 2 carbons here, so it makes no difference, which is why this example doesn't require any special thought. We do treat water like HOH, so that is something I'm going to write above just so we can consider it that way. That just helps us think about, if I break open that double bond, what are the two things going onto the carbon? One of them gets an H, one of them gets an OH. Again, in this situation, because there's only 2 carbons, wherever I put the OH, that would be the number 1 carbon. So it could be on the left or the right here. I just chose the one on the right. But if the carbon chain is longer, then we follow a particular rule, which I'll get to in just a moment. The last one I'm going to show you is the addition of a hydrogen halide. And again, this is a hydrogen with a halogen. And because we're putting on 2 different things, we have a star here as well. I'm going to start with a simple example, then we'll talk about the rule, and then I'll show you how that rule applies. So again, just keeping it simple with a 2-carbon double bonded chain, we're going to add an HCl. So I'm going to break open the double bond here, and one of the carbons will get the H, the other carbon will get the Cl. Again, because there's only 2 carbons, wherever I put the Cl, that will end up being my number 1 carbon, whether it goes left or right. And when, again, if the carbon chain gets longer, then I'm going to have to consider location, and we're going to follow the rule that I'm going to explain next. But for 2-carbon chain, this is all we have to do. So the rule I've been referring to is called the Markovnikov's rule, and there's a picture of Markovnikov sitting down there. When a hydrogen halide or water is added across a double bond, the hydrogen will attach to the carbon with the most hydrogens. So the rich get richer is sort of our expression. The substance that's richest in H's will get richer in H's. So I'm going to show you how this works, and again we'll go back to this rule. So when we talk about getting rich, we're talking about hydrogens. So all we need is actually one more carbon in our chain, and we will now have to consider Markovnikov's rule. So we often have to consider this because usually our chains are more than 2 carbons long. When I'm working with water, remember I'm putting on an HOH. When I break open the double bond, Markovnikov's rule will tell me where should I put the H. The carbon over here that's richest in H's, so when I say over here, I'm talking about this section here. The carbon that is richest in hydrogen will get more hydrogen. So the rich get richer. So the carbon with the most hydrogen gets the hydrogen. That means the hydrogen will end up going right there. So you'll notice that the OH is in the inside of the carbon chain, and you're going to see later on as we do other reactions, sometimes this is not where we want the OH to go. Sometimes we really specifically want it to be in a particular location. So Markovnikov's rule will sometimes get in our way, and we'll look at a way to overcome that later as we need to. Let's do one more example. This time I'm adding HCl, so again Markovnikov's rule will come into play because I have 2 different substances when I break open my double bond. In this case, again, the rich get richer, so this first, or you could consider it the last carbon, will be the one that gets the hydrogen. The one that's richest in hydrogen gets more hydrogen. So you'll notice the hydrogen is on the end and the chlorine is in the middle of the chain once again. Triple bonds are not as common as double bonds. If we consider what a double bond actually is, a double bond, we show just 2 lines, but really this is an electron pair. Oh geez, hold the phone. Is an electron pair. So we actually have 2 pairs of electrons in between this bond. That means that there's a lot of strain here, and so they are very reactive. Very reactive. And that means they're not very stable, not as stable as single bonds, so we wouldn't see them as often. Think about a triple bond now, and now we have, come on, Dot. Dot, come on, Dot. Oh, there we go. Now we have 3 pairs of electrons in a very squishy area. Electrons, again, repel, so this is extremely reactive. And they really don't want to be in this position if they don't have to be. They'll do it if they have no other option, but they would rather be singly bonded if they can. Now the exception to this, and I mentioned it when we were working with these, are benzene rings. Benzene rings, although we have double bonds every second, remember that the electrons are actually shared and constantly on the move. This makes them very stable, and they behave like single bonds. So we will not see benzene rings participate in addition reactions. They will participate in our next type of reaction called a substitution, which is what addition reactions or single bonds like to do. So working with triple bonds, you can control how much of the double bond you want to break open. So let's say, for instance, that I want to add a Cl2. And if I see the word controlled, it means I'm only breaking open, it was hard to see me do that, but I'm only breaking open 1 extra bond. So my final product still has a double bond, I've only opened up 1 of the extra bonds. If I have the word excess, or I might also say 2 Cl2s, those are 2 different ways to say break open all the bonds. So again, I can use the word excess or 2 Cl2s. I've just done the 2 Cl2s here, but you might see the word excess, and it means break open both of these extra bonds. So here, you're adding 2 times Cl2, so you have 4 Cls. So when you break open the top bond, you have a place for 2 Cls. You break open the bottom bond, and you have a place for 2 Cls. Our next reaction is called a substitution, and we're going to use substitution when we have single bonds. And that again is going to be a benzene as well. They are treated like single bonds. And this is like a swap meet. So 2 compounds form 2 different products. And so basically I'm going to swap one thing for another thing. And when I say one thing for another thing, it can be, it always starts off as an H swaps for a halogen. That's always the starting place. Once the halogen is on there though, I can swap it out for better things. I can swap it out for fancy stuff like this. There's all sorts of things I can do. Once the halogen's on there, I can swap it for bigger and better things, and it's just 1 for 1 each time. So this is going to be really important for making amines and also those primary alcohols. So Markovnikov's rule often foils us with primary alcohols because it always puts the H on the end. So this is how I can make a primary alcohol, because with substitution I can decide where I want the action to happen. So I can kick off a hydrogen anywhere I want on a carbon chain and replace it with a halogen, and then wherever that is, I can then replace it for something better. So our first move in substitution, if I don't have a halogen on there, if I'm working with just an alkane chain with just hydrogens, my first move is kick out a hydrogen with a halogen. Doesn't matter what kind of halogen, can be any kind. So this is our general reaction. We have some sort of carbon chain with an H, and again, there's lots of H's on an alkane chain, as we know. Our first move is always take a halogen. It could be a diatomic halogen, or it could be something like an HCl, something like that, or an HBr, whatever. It doesn't matter. As long as you have one halogen, you're going to do a swap. So one of the H's of your choosing will come off with one of the halogens. They're going to swap places. So you'll end up with a halogen now on your carbon chain, and the hydrogen will come off and partner with the other halogen. Let's do a couple of examples of substitution, starting with a propane chain. Again, I've done it structurally just so it's easier to see, and I'm going to start the process with a halogen. As always, that's the first move. So it can be a diatomic halogen or a hydrogen halide, either choice. I'm going to show you an example of a hydrogen halide, this one here. I get to target which of the hydrogens I want to pull off here. So I'm going to target this one, just because I've decided that's the one I want. And so it's going to substitute with the hydrogen. So the hydrogen will come off. I will have what's called a byproduct of H plus H, so H2, and then the chlorine will go on. So let's see what that looks like. So I have 2 products here, and the main one is the one with the chlorine on it. Usually that's sort of the first step with substitution, and I'm usually using it as a first step to try to get to somewhere else. I'm going to show you an additional step in a moment. The H2 is a second product, and we commonly call it a byproduct because it's not really the ingredient we want, we just end up getting it. So let's take that compound that we just made with the chlorine, and let's try another substitution. I'm going to show you a better substitution. So I'm substituting something that's bigger and better, and this is the whole goal of substitution typically. So the halogen is always your first move, but it's generally not your last move. Usually you actually want to get something on there, like this NH3. I want to get the nitrogen on the chlorine chain, or carbon chain rather, because then I can make myself an amine. So this is how amines are created. So again, I'm going to leave one thing behind, and then I'm going to swap. So you can see it's not always one element for one element, it's one thing for one thing, but it doesn't have to be one element for one element. I always leave something behind because if chlorine comes off, it needs a partner. Remember, chlorine's not stable without a partner. And also, if I were to take nitrogen with 3 H's and attach it to a carbon, nitrogen now has 4 bonds, but nitrogen only wants 3 bonds. So we always have to leave something behind. So NH2 will go on. I can collapse it if I like. I can keep the H's spread out if I like. It makes no difference. And again, I have another byproduct here of HCl. Again, it's a byproduct because it's one of the products I'm making, but it's not really the one I care about, so we call it a byproduct. That's how you would make an amine. Let's do one more substitution. Again, I've got the chlorine on there already, and I want to add something bigger and better. If I wanted to make an alcohol, what do you think I would add? We've actually seen this already. How do I make alcohols? So you would actually add water. And remember, water is HOH. And so the substitution here would be the halogen with the OH. So again, the OH would go on and the chlorine would come off and partner with H. So this is how I can make a primary alcohol if I didn't have an opportunity to make one through a different process. Substitution is always a good way to make an alcohol, any type of alcohol really, because you can target the H that you want to. And HCl, once again, would be a byproduct. The last type of reaction we're going to look at today is called an elimination, and it is exactly the reverse of an addition. So in addition, a double bond breaks open to make one product. Here, one reactant goes back to having a double bonded product, and there's two products. So one of the products will be a double bonded product. So it's exactly the opposite. This is one of the least used reactions. So we're going to look at 6 reactions altogether, and really there are 4 that we use a ton. This is one of the ones that we don't use very often at all because it doesn't really go anywhere. It's sort of a single step and that's the end of it. So for this one we have one reactant, and usually there's something on the carbon chain that's obvious, like a halogen, maybe an OH group, something like that. And you're basically going to take 2 things off, and what will happen is the double bond will collapse down because you don't have any more bonds, so you have to make a bond between carbon itself so carbon can be stable. So again, it's the exact reverse of an addition, because we'll have a double bond here being formed, and then we'll have this XY, whatever it happens to be, as a second ingredient. So if you were to read it in this direction, it looks exactly like addition. We have a double bond plus an XY, making a single bond with XYs on it. So this particular reaction, I've got a 3-carbon chain with hydrogens and a bromine. On the arrow, I've got H2SO4, it's acting like a catalyst, and underneath is a triangle. That actually means heat. And the reason why I need these extra ingredients is because an elimination reaction is not generally a productive reaction. You're going from something that's more stable to something that's less stable. So it sort of goes against the principles of the universe in some ways in terms of getting more disorganized. That's a bigger conversation. But because it's not a natural reaction, I have to sort of force its hand a little bit. So the way it will work is bromine is definitely be part of it. In this case, because it's right in the center, it doesn't really matter, but you need a partner on one of the neighboring carbons. So you need a hydrogen. So I'm going to just take this one. It could be the one on the right as well. You would find in this particular example, because it's a short carbon chain, it would end up being the exact same thing regardless. So I'm going to pull those guys off. When I do that, carbon won't have enough bonds, so it will collapse and make a double bond with itself. So I'll end up getting my double bond here, and my H's here. Everything else will stay the same. And then that HBr will be one of the products here. So that's where we'll leave off for today. And tomorrow we'll learn the other 3 reactions. And then next week we'll be looking at how do you put one reaction after another. We had a bit of a preview with that in the substitution section when I added the halogen, and then I took the halogen and added the amine. But we'll be going in that direction a little bit later on.